Question 1 for me. What you big on see? A uniform ladder, Wait. Wait, 120 Newton, Rest is 1.6 meter from. Even at the tenable problem. A uniform ladder 4 meter, weight 120 Newton.
Rest with each foot 1.6 meter from the smooth wall. Find
Okay, so reaction of the wall and normal reaction. Madam, can you hear me? There is something we call pay attention. Then everything is not how will you or what if. Pay you go the attention first. Whatever, how will you know? Why are we not here? See, ladder by ladder, whenever you bend ladder, if you look at it from the side, you're noticing that it is leaning. So this is the wall itself. So that is what I drafted. And this is not something you say, what if I see another one and it's not looking this way? If it's not looking this way, you will still see that it is still maintaining the same shape, just that the angles might be too close or too far. But it will always take this shape. You need to know that. And remember I told you that whenever they give you this question, if they tell you angle is made with the vertical, that it is here. If they tell you with the horizontal, it's here. But if they did not tell you angle, you just know that you're talking about what? I said something like that, shouldn't it? Yes. So if that be the case, they are telling me that this ladder rests on this wall, and then with each foot 1.6 meter from the wall. So once I see this thing, if you notice, you'll see like it's more of me having something like a right angle triangle. But right here, I am having distance here, distance here. That is distance on the z-axis, distance on the x-axis, but I don't have distance on the y-axis. These are the first things. That's why we started with vector. So there are some things I want you to always think of first. So this, what we are doing now, is more like, or should I say, I want you to take it as the first things to look at. So I have the z-axis having 4 meters. The x-axis having 1.6 meter. But we know that when we did IJK vectors, we have I for x-axis, J for k-axis, and J for y-axis, Shebi, and K for z. So that means that y-axis now is what I don't know. So if I don't know y-axis, the only way to get it is by doing Pythagoras. So I'll say using Pythagoras. So if I'm using Pythagoras, I will now have that. That is this side now. Really? So 4 squared. R squared is equals to A squared plus B squared. So equals to, the A is the X. X always comes before Y. 1.6 squared plus the Y-axis, I don't know it. Please, those questions, like questions we are solving, are questions that I want you to learn. Then when you go home, as we send that past question app, you go through it. Try to start for questions that look like it from that past question app. It's in solving questions. If you learn a topic, you don't go and be reading the GST parts over and over. It's wasting your time. What you need to be doing is to check the questions, look at it, solve different type of questions like that. That is how you learn physics. Physics is to know the concept and how to solve questions. So 4 square is what? 16. What about 1.6 square? 2.96 plus y squared. Okay. This thing, if you cross over, we have should be minus.
Yes.
Equals to y squared. So we want to subtract it for me. What do we have? 18. 13.44 equals to y squared, should be? So I can say take the square root of both sides. So that y will now be what? I have what for me? 3.66. And you know that this means that y is approximately 4. Do you agree? I remember that this thing is in meter. This one is in meter. That means this is also in meter. So I'll come and put 4 meters. Do you notice the first step? Are you noticing the first step?
Yeah.
The first step is that I am trying to make sure. The first step is that I am trying to make sure that I have the x-axis, the y-axis, and the z-axis. And if that be the case, I am gotten that this is 4 meters. That's the first step. That is not what they asked me, but I got it because I know that this can help me. Why? How does it help me? Notice that they did not give me angle. Shibi? Yeah. They did not give me angle. And anytime they did not give me angle, once I know the 3 sides, I can easily use the tan rule. Are you seeing it? So I can easily use the tan rule. So my second step, I can easily use the tan rule. And tan rule is simply tan theta is equals to y over x. So you know that this is the same thing as slope. Are you aware? Yeah. I can easily do it. So second step is that I'm using the tan rule to find angle or to find theta. I hope you know that. Anyway, when we get to circular motion, we start doing that one. Let's not add to your confusion now. So tan theta equals to y over x. So, but what is our y? What about our x? 1.6, right? Okay, tan theta equals to. So, if you check your physics workbook, even not just the past questions that you see there, you see all those linear ladder problems there. Once you've learned all these concepts, it will be easy for you to solve. So now do for me 4 divided by 1.6.
2.5.
2.5. Is it what you have? Equals to. So if I make theta subject of the formula, theta will be equals to tan of 2.5, right? One punch it for me. What do you have? 68.19 like this?
Yes.
Okay, that is approximately 68 degrees, Shavin. Okay, that means I am having theta to be approximately 68 degrees. Okay, so I can say that my theta here is 68 degrees. Shavin and I did not start with this. So when you finish, you can draw another thing. You can draw another one and then put your 68 degrees. I've not gotten to the part of if. I'm still teaching. So please, pay attention. I've not gotten to. What you are doing with that if is that you're taking us back. When I get to the part of if, I'll make room for that. So, copy. I want to clean. And the only way I allow was in a class, it was a joke. We're not joking here. I will have room for question. It's not time for question. Now it's time for learning. I'm the one to tell you when to ask question. I have time to work with today. I noticed that most of the time we spend time solving one question, even as a question. Oh yeah, can I clean? No. What I'm teaching you now is I'm telling you, these are concepts, manage these concepts. When I now make room for you to ask questions, you now ask me questions. I will not answer you. But for now, what I'm giving you, this concept, know it. Once I'm giving a question and they did not give me an angle, it's not just about linear ladder problem, because some of the time we think maybe we solve something, that knowledge is just it. But notice here I am applying the knowledge of vectors as well. So they are related. So anytime you are solving any question, it's not just here, but in physics, you notice they did not give you angle. The next thing to check is the sides. Once you're able to get the sides, all you just need to do is to now use tan rule and get your angle. That is what I'm just doing here. I've not started solving linear ladder problem. So it's not just about linear ladder. Every question in physics, you need to know that. So because angle was not given, I do this. Now, I will go back to that my linear ladder to redraw it. Let me just draw it. What we call free body diagram, or you call it the vector diagram. Okay, this one. Okay. Now, please, this is where we now start the question. In starting the question, let me draw my ladder. Let me draw the wall. Let me draw the ground. You see that it's not like I'm forming this thing. It's just natural, nature. So if the ladder is leaning, automatically if it's leaning on the wall, the ground itself gives it a base. So it has formed something like an inclined plane, or you say like a triangle. Now, if I know this, the next thing you need to ask, please, I want to ask you now is, tell me the force is acting on this. Use your hands and be pointing out. Okay, the weight of the ladder itself, Shirin? Yes. And you know it's weight of any object acts towards the center. Yes. Unless you are told different. So if it's acting that way, we call this weight, which is equals to mg. Okay? Weight equals to mg. Okay, which other force? Any object, just the one I'm standing now, there's a force that tends to. If you want to know it, when I start teaching you dynamics, if you bounce a ball on the ground, if there's no force there, notice, if let's say I carry the ball and I bounce it on top of water, or let me use something like a Dunlop, if you bounce it, if it's Dunlop, it will tend to bounce back more. The same thing with if I bounce it on the floor. But if you bounce it on water, maybe a very muddy water, you bounce it. What it will do is that it will splash the water, but you just circle around. Is it not true? Yes. But if it's maybe your normal water, if you bounce it, up thrust will tend to throw it back. Not like it will throw it out. But what up thrust is not saying is that as it's trying to throw it out, that even if it doesn't throw the object up, that you shouldn't be checking out the object, but rather be checking the water that comes up. You understanding it? That one is for up thrust. So it's the same thing, but when it has to do with fluids, you are not checking the object bouncing back up, you're checking the water bouncing back up. But when it's the object on normal ground, he's saying that if you throw it, check if it bounces back. And that thing is what we call normal reaction. We call it N. So we are saying that every object has a force tending upwards. That is N. Now the next thing is that as this ladder is leaning on this wall itself, assuming there is no force holding this ladder, what will happen is that as this ladder is leaning on this wall will just collapse. The person are questioning, God forbid. But provided there is force on it, it simply means that there is a normal reaction from the wall. You can call it NW, but me I like to call it RW, reaction of the wall. And if that be the case, notice that this particular ladder being here, do you know that there is a way you can place this ladder? Let's say, have you ever, yes, we've seen it most times, where people will be walking down from staircase, they just sleep. It will give them so much injury, not just small injury. They will even have to go and do bandage, and they carrying their leg. The same case can happen here, assuming this ladder does not have friction. Notice that as this ladder is this way, the ladder itself can slip this way now. But because there is friction going this way, the ladder will maintain balance. So we are saying that there is a force going this way, which we call the frictional force. We use small F for it. So if I know that, let's say, because of your level, they don't include friction of the wall. But assuming they said that the wall itself has friction, or normally, we're not just talking about your level. Now let's talk about reality check. Normally, when I place this wall here, this ladder here, the natural thing is that this ladder could slip from this angle as well. I can have this ladder as is this way on this wall. If it doesn't have enough friction, this ladder can slip like this. Are you aware? Yes. So if that be the case, for the fact that this can go this way, that means that there is a frictional force on this as well here. So we also have this way a frictional force, which is making it, as the ladder wants to turn downwards, the friction is going upwards. So on a normal, these are the forces acting on anything leaning ladder. But when we come here, we are saying that when it's frictionless wall, we are ignoring this friction. We are acting as if we don't know that friction is acting on this wall. So, and this is the kind of question we are given. I ask. Is it this one? This one? Okay. This is why we spent 5 hours, 2 questions. Oh yeah, see now, see. Because everybody wants it to be clear. And I want it to be clear too. But we won't entertain what if. I'm answering him because he said, can you explain? He did not say what if. Oh yeah, see. If I have this wall, and I have my ladder on it this way. Let's say there is no friction, or maybe I carry red oil or grease. We know that there are things used to reduce friction, is it not true? Which we call lubrication. Let's say I come and lubricate here, pour oil, pour things that, like all those things we use to treat ball and roller bearing. So if we pour it here, you notice that if I place this ladder here, no matter how I place it, the minute I try to climb, what will happen? Shaving? Yes. You just do like this, come down. So what we are saying is that for the fact that this wall, we are considering it to be a rough wall, that this wall is steady, there is no oil on it. What we are saying is that if you really want to look at things properly, that the fact that this ladder is not falling down from this place, coming down, that there is an unforeseen force, or there is a force, an invisible force that tends to pull it up. And that force is called frictional force. So it wants to come down, but that force is keeping it up. So, but we are not saying that when we are treating this, like the question we are giving, we are overlooking, we are taking it that this wall is frictionless. So we are overlooking the effect of friction on the wall. So if that be the case, what we are now saying, in simple terms, using the same principle I taught you the last time, I told you that whenever you are treating leaning ladder problem, that there's a shortcut. But we'll still do that one we did that day, just for the first one, then we'll start using our shortcut. I told you that whenever you are considering the y-axis, just say torque times cos theta. You know that normally y is supposed to be sin theta, should be? Yeah. But when we are considering leaning ladder or inclined plane, especially leaning ladder, we just say that y will become torque. And we know that torque is simply, torque on the y-axis is going to, torque is simply RF, is it not true? Yes. Now put cos theta to it. Why the x-axis should be RF sin theta. This is the shortcut. If you don't even want to suffer, but remember that the arrow here, when we are dealing with linear ladder, is length and not radius. Hope you remember. Yes. So for that reason, this will be something as saying LOF, or you say FL cos theta, and this one will be LOF sin theta. So this and this are the same thing. This is the same thing. So if you don't want to do all the things we are going to be doing now, trying to stress about ourselves, rotating it, you can just stick to this. Once the question is given, you just do this thing. You just look at the y-axis facts. Don't even think about it. Don't say what if. Don't say how about. Just, if it's y-axis, just use this thing. If it's x-axis like this, horizontal, just use this thing. You will get it. There is no guessing. But we will do this first one using the normal method. The second, the third, going forward, when I use our shortcut.
But Uncle, the angle will be on top.
Which angle?
For this formula.
This one?
For this formula. For this formula now.
See, as this thing is 68, there is nothing like angle being on top. You are going to be using your experience of breaking down angles. You don't do manipulation here. So, as this thing is 68, the total angle here is 90 degrees, Shebe? Yeah. 90 minus 68 is what? If I remove 68 from 90, what?
22.
The angle here is actually 22 degrees. It's up to you. Whichever angle you want to use is your own business. No manipulation. And you know that, are you aware that if I have something here, that this angle here is also here? Yes. Alternate, Shebe? Yes. Yeah, I don't want to be going there. But just have it in mind that what you are using is simply you maintaining these two. It's either you use this one if you want, because whatever you use here is the same thing with when you use it. Now yeah, let's solve this question using that our normal method. Number two, we now use our shortcuts. So to solve this using our normal method, we'll simply do the first. We said that the first thing we are supposed to do is to come and redraw this. As I've redrawn this, I want to say everything here using equilibrium is also here. So you see, if I teach more, I look at you. Then everything here is also here. Do you agree? Now notice that if I have an angle here, watch out. Here the knock are more like I now have like turned upside down. So if I carry this thing and let's say it's my compass I'm having and I turn it, you see that it will still maintain this shape, is it not? Which means that the angle I have here is this angle. Another way to look at it is alternate angle. This should be here. Are you seeing it? Yes. So if I know that, this is the normal method I'm teaching you how we derive this thing. But I told you, never go into the hall doing this nonsense. We have a waste of our time. But just for the people that are not in class. So let me write that 4 meter. Let me write that 1.6 meter. Then let me write that 4 meter that is here. Now remember that this one is 120, Chevy? Going down 120 Newton. So if I know this, what I'm saying now is, let's say, do you remember that when we drew this, we said that this side is the reaction of the wall. And this side is the normal reaction. Do you agree? And we say that down here, somewhere here, frictional force is going this way. Yes. Now, if that be the case, I want you, remembering what torque is. Torque is simply product of perpendicular distance and force. Or you say product of distance and perpendicular force. Right? So, perpendicular means at 90 degrees. Now, if I want to find this RW, notice that this thing is more like this. This is the force. See? Now, the ladder is the distance. So, it's looking like this. Is it not true? Then I have the angle here. But our goal in finding torque is that we always make one side. Do you remember? When I'm looking at RW, I have to make the other end the pivots. You catch it? So this has to be my pivots. That is the side that is not torque. It's more like this side now. That's the force I am applying. This force I'm applying has to turn this side. Just like when I told you, when we started, I said, if I have the door and I come and I want to open that door. So as I'm opening the door, you see that there is a part to the pivots that is doing the rotation. That is it. So if I'm going to be applying force on this RW, it simply means that this side becomes the pivot, the side that will be turning. That is what torque is. So if that be the case, torque simply says, how do I get this now? So that the ladder moves from that way to 90 degrees. I want it to be this way. This is how it should be for me to have torque. That is force and perpendicular distance. So how do I make this now? This thing that I have here. You notice that it's not at 90 degrees, Shelly? Yeah. So if I'm pulling this thing now to 90 degrees, this side, if I'm pulling it, this angle, will it be opening or closing? Opening. It will be opening, Shelly? Yes. And we remember that away from the angle, we use what? Sine. Away from the angle, use sine. Towards the angle, use what? All science students take off. This thing is very popular something in secondary school, unless you went to your own type of secondary school. But I know that then they do it well. So, away from the angle is popular. I did not invent this one. Use sine. Towards the angle, use cos theta. So all science students take coffee. And don't say you should go kill yourself with coffee. No, so for that reason, if this is L now and I'm opening it, it now becomes L sine theta. Is it not true? That is length now. To take it to 90 degrees will be L sine theta. But remember that RW now is the force. Is it not true? So I come and put my RW to it. So that means this is the something I said force and distance, then sine theta. That is, for it to go to 90 degrees, it has to use that theta, sine theta to do that. So, opening it to be this way. So that means that is why I said, whenever you're doing horizontal, don't suffer with doing this nonsense. Just horizontal will be torque and sine theta. Vertical, whether up or down, will be the torque and cos theta. That is how we'll be solving it. We don't have to be proving over and over. So, but let's prove this one now. So, if I want to find something like
normal reaction.
Should be this one. Yeah. Normal reaction. Naturally, anytime they give you normal reaction, if you want to solve for it, you have to have two things in mind. One is that you remember that upward forces, upward force is equal to downward force, Shebi? Yes. And if upward force is equal to downward forces, it simply means that check upward, Eva. On the total of upward, downward, Shebi? Negative axis of X now, horizontal. Don't forget, So the upward is what? Is equal to what? So please, before you start solving for normal reaction, unless they did not give you weight, but I will solve for normal reaction, reason being that I want you to see how we derive the angle. But if it's a question like this one, just first thing you need to think is that since N is equal to W, and W is equal to 120 Newton, that means that N is simply equals to 120 Newton. You don't have to solve anything for the N, very simple. But if I want to prove it, like let's say, get how we, should I say, y that is vertical is cos theta. So that is why I will not do this now. Notice that if I look at that thing well, let me take the force away. And take the ladder. You see that this is N, and this is that ladder that is 4 meters. Is it not what you're saying? Yes. So if this is what I'm saying, notice that there's an angle here, which we'll call theta, Shebi? Yes. And if that be the case, notice that there's an angle here, alternate angle, which is also theta, Shebi? This angle is equal to this angle. Do you agree? Yes. Now, for any, because what we are dealing with is torque. We are not just dealing with force, we are dealing with torque. For us to have a torque between this force and the distance, that is the distance, the length here, we have to make this end the pivot, because we are talking about this. And if we make it pivot, what we need to have for this force to have a torque is a situation where this force is like this, and okay, let me do it up. It's a situation where a situation, we've copied this one. A situation where I will have the N this way and the ladder to be this way. So that by the time you check it, you've gotten that 90 degrees. So what I need here is simply, how do I make this thing now? How do I get this thing that I'm seeing here? How do I get this thing now to come here? Are you seeing it? That is what torque is. Remember I told you when we started that if it's moment, that moment simply talks about product of perpendicular distance and force when it is not in continuous rotation or continuous motion, Shebi? But that of torque is that you are considering it that even if you remove that force, the thing can keep rotating itself. The force is still being applied, rotating. So that means that if I ever want to talk about torque, my mind should be telling me that as I am applying the force and I'm making this the pivot, it simply means that I have to rotate. And if I have to rotate this, you don't rotate and start going 180 degrees, 270, 360. What they are asking is to rotate to 90 degrees. That is torque for you. So how do I make this? Well, you now, if I say I don't want to go this way, let's not argue, and I want to take this thing like this. Is this still torque? No. Let's say as this thing is like this now, I say that it's like this, I don't want to come like this. So what if you come and rotate it to come and it's no longer torque now? There is no torque there. Once you are having the force and the distance in the same direction, it is not torque. Torque is zero there. You understand? Once force and distance, they are in the same direction, the torque is equals to zero. So if I know that, the only way I can be able to get a torque for this is taking this thing now to this axis. And notice that if I'm taking this now to this axis, this angle, is it going to the angle or away from the angle? Should I will be closing this angle? Yes. So if I'm closing, if you still want to argue it, Shebi, you know that what I have here is also what I have here. Yes. Do you agree? Yes. If, let's say, I consider any this way, because this and this are equal, and I have this thing this way, and I have this. The only way I can get a torque, and there's theta here. The only way I can get a torque is when I take this thing to this place. Is it not? And if I'm going this way, it's closing the angle, Shebi. So however you go, you see that the only way to get this is when you're going towards the angle. That means that whenever it is vertical axis, you should just consider it torque and cos theta. So for that reason, since this is L, I'm going towards the angle, I'll come and write L cos theta. And we know that torque is product of distance and force, perpendicular force. So the force there is N. So N L cos theta. Very simple. So what I'm saying is that as my students, I don't want you to be inside the exam hall. You are doing this thing, suffering yourself. Just once you see it, however they want to do it, once you've drafted your diagram, done everything, just come and remember that x-axis should be this, y-axis. So please, talk on the y-axis, let me hear you. Talk on the x-axis. Talk on the y-axis. Talk on the x-axis. Very simple. Another way to remember it is that academically said that simple pendulum, once a simple pendulum, once is simple pendulum, once is that our relative motion, once is inclined plane, we'll still do inclined plane under dynamics. Once you have these three concepts, that y-axis becomes cos theta, and anything you are doing with x-axis becomes sin theta. Reason being that you are taking it that you are viewing this with angle made in the resultant. So if that be the case, you need to know this. So with this said, let's now go and tackle that question. I don't have to draft this again. Let me just use the things I know and see if we can solve the question. Okay. So we won't be doing come and draw. What we are just using is any place for vertical, do cos. Any place for horizontal, do sine. Alright, to find RW now, RW will simply be what? Is horizontal. What am I doing? RW times the ladder, shall we? Because it's horizontal, it will be what? Sine theta, shall we? Yes. Is equals to, so what you will be doing, you now say sum of the horizontal force is equals to the sum of the vertical forces. Now please, what are the vertical forces here? Please, do you remember when we started that RW is equals to FF, shall we? Yes. There's no need finding FF when we have RW. Do you still remember that N is equals to W? Shall we remember? Yes. There's no need finding N when we have W, and there's no need finding W when we have N. That's what we mean. We can just use one of it. We are now saying that to find the torque now, sum of torque on the horizontal should be equal to sum of the torque on the vertical. So horizontal, I'm seeing RW, shall we? Yes. Hope you know that it's the same thing as saying, if I don't use RW, since I'm making this one pivot, assuming I make this pivot, it will now be frictional force L sin theta. Are you aware? Yes. Because it's horizontal. So, but since I'm making this one the pivot, since I'm making this the pivot, so I have RW sin L sin theta equals to the vertical components there. MGL over 2. MGL over 2 cos theta. Like this, shall we? Yes. Do you understand why it's L over 2? Yes, because the weight is acting at the center. Yes. So weight always acts at the center. So it's actually happening at the middle for that weight. So the length, when you're considering that mg, that is this weight, is actually, as it's on it, it's affecting it from this end to this end. So I have that. So in built, I now have RW, L is 4, shall we? Yes. My sin theta, what did we get sin theta? 68. Equals to mg is 120. Then 4 over 2, which is 2, shall we? Cos 68, right? So if I know that, that means that I'll do 4 sin 68. Do for me 4 sin 68. Punch now, punch. 4 What's 68?
3.71.
So I have minus W
71.
3.71. Give me in 4 decimal place.
3.7087.
87. I'm not the one that taught you to approximate when you've not gotten to your final answer. If you're approximating or when you've not gotten your final answer, you make sure you do it to 4 decimal places. It's your final answer, you now approximate to anything you want. That is what I told you. So you don't change your answer. Oh yeah. This is 240, Shebi? Cos 68 and it's in degrees. So somebody does not forget. So I punch for me 240 cos 68 degrees.
It's 9.9056.
9.556 like this. And it's equals to RW 3.7087. Now you can see that if you want to make RW, so you have
90.
okay, like this.
90.
Yeah.
9056.
Okay, 956 like this. But please be checking though, because some people's calculator is no longer calculator. They've removed what is the calc inside. It's now letter. Or is it letter? So divide both sides by 3.7087 for me. This will make this to get out. So that reaction on the wall is equals to a punch for me. 24.24 like this. 1.8. So which means the reaction on the wall, or normal reaction of the wall, is simply 24. And notice something. We are talking about force here. I hope you know. That means that the unit is going to be what? Unit 2. So you are solving number 2 for me. So please, relax. Remember they asked me to find n. So n is simply equals to 120. Ask me. What of what? This 22. We just put it because we want to say angles in a rectangle, triangle. Because we have 90 degrees, we said since we got this one to be 68, that means that here forever, with 68, that is 90 minus 68, we'll not put it. It's of no use. Even if you use the angle on the vertical, you still get the same answer. Provided you use it well maintaining this, you still get the same answer. You see that you can, what did I tell you the last time I taught? I said, if they gave you angle, if they said horizontal, you use with the horizontal. If they said vertical, you use vertical. But if they did not give you at all, you use horizontal. That's what I said now. That means you did not hear me.
Yes.
Yeah, please, I will say it again. If angle is given, they said, and it made angle with the vertical. You know, or they tell you it made angle with the wall. It's the same thing as saying made angle with the vertical. If they don't tell you made angle with the ground, or they tell you made angle with horizontal, it's the same thing as that normal way. But if they did not tell you where angle was made, you are using your angle to be made with the horizontal. So that's why me teaching you alone, I teach it on the floor. Me teaching you alone does not guarantee that you plant it. So on a day like this is an opportunity for us to test if you plant it. So you can try the second one. Then before we try it together, see what you can do. Let's try to tackle. It's not every time we come, we start teaching fresh topic. Today let's solve questions. Let's see how much you grab before we go for us. So this is time for question. It's now this time that all the what if can come in while you are solving number 2. What if? Or if? So you can now ask me. Okay, you don't grab that one. But only I'm going to explain it for you now using another diagram. The goal of this class is your understanding. Now see, watch. Shebi, this is the ladder. You understand this one? This is the wall. This is the ground. Watch. And the weight is acting this way. Shebi, if this weight, please watch. If this weight is acting this way, do you know that if I extend this weight is still acting, I don't know how far it goes to the ground, but that way it is acting. Now notice that I've been able to divide this now into 2. I can say, let me carry this thing now. But I'm seeing it as this way. If I carry it out, this is now 2. I say it. That is, the total of this is 4 now. This is now 2, and this is 2. I see it. Now, as I've carried it, I can say that if that is the case, the same thing I have here, by equilibrium, we know that it's also here. That means I now have another one that is up here. So 2. And you know that it has divided this horizontal into 2 as well. So if that be the case, what we are looking at is that whenever we talk about weight of something, the weight of something, we are saying that it acts through the center downwards. So if that be the case, this particular ladder is feeling the weights down this end, on this end. And the impact of that weight can also, if I want to consider it, is also acting this way on its own end. But not completely that the two of them are being affected at the same time. So if that be the case, what we are saying is that when I am considering weight, I should always make, unless specified, unless maybe they tell you that a man now climb this ladder. And not, they say a man climb this ladder this way. You will not see that the weight acting on this ladder will now be the weight of the ladder and weight of this man. So what I will now check is how far, or should I say how far from the ground is the weight of this man acting. So it can be maybe 1/3 or 2/3 or whatever it is. So whatever it is, I will simply times it. If it's 2/3 from the ground, it will simply be 2/3 times the length. If it's 1/3, it will now be 1/3 times the length of this ladder. Are you seeing it? So, but the main thing is that once you've been able to pick it, you will now go back and remember what torque is. And that torque is simply distance and force. But this thing is only when it's at 90 degrees. A situation like this where the distance is not at 90 degrees, you must introduce components. Just like when we do resolution of vectors. So you must introduce components to show that you are taking it to 90 degrees. So we are now saying that if I now want to take this half that I have here, let me now break down. If I now want to take this half that I have here to 90 degrees, notice that this becomes the weight, W, Chevy, and this becomes my theta, and it's still my theta. Let me redraw. I have weight, theta. That's my 2, which is the same thing as I've divided the length into 2. L over 2. So if I want to check this now, and this one is acting this way. So if I want to get this W, notice that this is the same thing as saying I have this like this. Notice I have L over 2, and I have the weight. So the only way to get this thing now to have a torque, the only way to get this thing to have a torque is when I now have it this way. That is this ladder now, this L over 2 has to come this way so that I can have 90 degrees. So if I want to get that 90 degrees, what I will simply do now is to simply say, the angle I have here, theta, Shebi, you know that it's also here. Shebi, it's also there. So if I want to take this thing now from here to this place so that I can achieve this, it is not at 90 degrees, but we want it to be at 90 degrees. Always eat before coming. So if I want to take this thing now from here to 90 degrees, that is so that I can get this, because this one is already vertical, to get this. Am I going towards the angle or away from the angle? Look at it well, look at it well. See, this angle is here, Chevy. This is what I want to achieve. This thing is what I want to achieve. So that I'll be able to say that it is now force times perpendicular distance. But this is not what I have, this one is what I have. And the only way to do it is that I cannot take the force, but rather the length. If I want to carry this length now, so that I will go to the horizontal axis, this angle being this angle, am I closing this angle or opening it? Closing it. So you see that by the time you take this now, you are going towards the angle. So for that reason, I'll simply have W. This W. That is what torque is now. First, so W, and the ladder I'm taking now here is L over 2. Times L over 2. It is going towards the angle. It is closing it. Because theta is towards the angle. That is why I have this. This one. If I'm considering, see now, if I have this, and this is RW, and I know that if I have this to be theta, this angle is also here. Alternate angles. You remember, alternate angles are equal. So I'm coming. So if that really the case, I will now say this thing that I have here is looking this way. The ladder itself is the full length. It's L, RW. This is the way it is. But in order to achieve top here, I need it to be in this position. 90 degrees. So how do I take this thing now from here to this way so that it will give me this? So that is to drag it this way, shall we? And notice that if I drag it this way, this theta, if I drag it this way, it will be opening this angle. It is going away. So it's simply going to be the RW and the L, because it's opening, going away, sine theta. I say it, but what I'm saying is this. I'll still post the video, but what I'm saying is, let's say this thing now, you doing this thing is inside the exam hall. It's you wasting time. What you just need to be doing for me is that once it has to do with linear ladder, that the vertical axis, the y-axis, is simply the torque you are talking about. Anything you see maybe coming down, straight down, or maybe going up, straight down. This is the way it can be when it's linear ladder program. So anything you see going up or coming down is y-axis. Just say that's my force, that is the force which is going down or coming up. And that's ladder that you have itself, which is the distance. So torque, then y-axis normally should be sine theta, but rather change it to cos theta when it's running another program. So that is why I now gave that the torque for the y-axis should simply be torque times cos theta. And for the x-axis it should simply be torque times sine theta. Is it for which one? Yes, now for weight. The weight acts at the middle point downwards. Is it for when I'm doing the direction of the wall? No. Hey, God. Blood of God. See. Let me connect. Make sure you are solving something and this one does not concern you. Some of you eat in the morning before coming a water, a tiger you come to school and you want to be strong. No. Save your money. You eat rice. You eat upper. The day there is no rice, you eat upper. And therefore that you have your which one? The first. This one. Remember that early is for the ladder now. It's for the ladder. I'm coming. No, wait, you did not approximate your goal. I forgot 3 points. You use 3.6. What if you use all the things in 4 decimal places? It's better than you using 3.6. Let's see what you have. Let me answer in the comment. Okay, go. Hey! Lord of Jesus. Length of the ladder, is it not the same thing? Length of the ladder is 4, they gave me here now. So if I have L over 2, simply the same as saying 4 over 2. Ask. Wait, I'm coming. Let me explain this to you. and look at that linen ladder problem, you will see the reason why it looks as if it's difficult for students. It's simply because it needs your attention. And once you pay very much attention to it, it will become simple going forward. I'm coming.
Sir.
I'm coming. See, watch. Let's not do it a small way. I have the ladder. This is the total length. If I have this to be the center, this will simply be L over 2. L over 2. L over 2, L over 2. That is half of the ladder, and half of plus half of the ladder is equals to 1 of the ladder. Chevy?
Yes.
If that be the case, if we come and see that there is weight acting downwards, it simply means that if I choose to say this thing going this way, what I have here is also here. So this is the same as say I have this now, and I have this up here. So the only length I'm considering here for the ladder is simply this side. So this is L over 2. L over 2. The only length I'm considering here for ladder is simply this L over 2. Any other thing outside here is for wall. This thing is for wall. This thing is for ground. This is ground. This is the wall. This is the ladder length, or the ladder. Are you seeing it? That it came before doesn't mean that they are the same. So if that be the case, what we are not saying is that maybe there is a force we know that is acting here, which we call RW. Now, if this RW, for example, watch out. If this RW wants to, let's say we apply force on this, so that it can rotate 90 degrees and we make this thing pivot. Pivot simply means that if I apply force here, that I want this thing to rotate to 90 degrees. Now, if this thing is rotating to 90 degrees, and I apply force here for it to rotate to 90 degrees, let's say I drag this thing and it rotates to 90 degrees. Then, if this thing is rotating to 90 degrees here, what we are saying is, the whole of this thing, will it be the whole of this thing that will rotate for these pivots? Like, I apply force here. Watch out. I apply force here. Will the whole of this ladder rotate? Because it's at this pivot now, shall we? Yes. But notice that when I have this weight happening here, at this center part, if I apply force on this weight so that it's come here, this thing, the weight already is at the half part of it. Will the whole ladder come with it? The part that we turn is the part from that weight to the pivot, which is this now. Is it not true? So this part will not have business with it. But if I apply that force, the part that will rotate to get me to 90 degrees is simply from here to the pivot. That is why we started with calculation first. So know that. Let's look at the second question. We don't have time. If you are through, let me see your work. Make sure you are trying. I'm coming. Make sure you are trying. I will solve this one. Let's see. I'm coming. Look at everybody's work. Okay, we'll check. Make sure you're not copying from anybody. Okay. How can you do? We'll check. Okay. I'm coming. I'm coming. You try. You really try. You have the idea. I'll check everybody's work.